Hi guys, in this video we'll begin our look at substitution reactions. This handout here, my copy is pink. We'll be looking at SN1 and SN2, and on the cover page here these are some warm-up questions. The types of line reactions that we'll be looking at. And for each of these, you should provide a detailed stepwise mechanism. So, let's look at this handout. Title here, Nucleophilic Substitution at a Tetrahedral Carbon. Chapter 7 in the Klein textbook. Okay, substitution reactions. This is a general line reaction which shows substitution. We're going to have a tetrahedral carbon with a leaving group, denoted here by X. Leaving group I abbreviate LG, many do. And the leaving group is going to leave the molecule. That's why we call it a leaving group. It will be replaced. It will be substituted by a nucleophile. In this reaction, the nucleophile replaces the leaving group on the tetrahedral carbon. We could call it a replacement reaction, but instead in organic chemistry we call it a substitution reaction. And then the leaving group has left. Now in this general reaction, it has taken on an additional lone pair. I'm not showing full lone pairs here. The nucleophile lone pair is what is now bonded here to this carbon as a bonding pair. Okay, we will see this more. This is a general introductory line reaction. I make a statement here about the leaving group. It must be electronegative enough to take on an extra lone pair, which usually leads to a negative charge, but not always. Now halogen we will see is our best leaving groups, with iodine being the best. Iodine is better than bromine. Bromine is better than chlorine, and chlorine is actually much better than fluorine. But other types of atoms can also be leaving groups. Substitution reactions will always have both a nucleophile and a leaving group. Now note, previously with alkenes we looked at addition reactions. Something added to the molecule. In those reactions nothing was replaced, nothing was substituted. Here we're replacing a group, and that's called a substitution reaction. Okay, a more precise example. You take this alkyl bromide and hydroxide, we can get a substitution reaction. The hydroxide can replace the bromine, or bromide if you want to call it, because the hydroxy group, the OH, is now bonded to the tetrahedral carbon, and the bromine has left. It took on an additional lone pair. Here there were 3. Now there's 4. It took on an additional lone pair. Now it's a minus, and now we call that bromide. And thus we can, over here, we can talk about how the bromide is the leaving group here. And the hydroxide is the nucleophile. So a standard substitution reaction. Okay, let's give a mechanism for this reaction. We're actually going to show 2 different mechanisms. Then we're going to step back and say which one seems to be most reasonable, and ultimately which one is correct for this example reaction. Okay. let's propose a mechanism. The bromine has to leave. Hydroxide has to bond to this carbon. How could we do this? Well, what if we just have this bromide, the bromine, just leave? These electrons move on to bromine and break away from that carbon. That would give a carbon with only 3 bonds. There's 2 undrawn H's there. That would actually be a carbocation. And the bond was broken. The bonding pair moved on to the bromine to become the 4th lone pair. And we could show one of the products, bromide. So this mechanistic arrow would provide one of the products, but also a carbocation. Now we'll come back and address this carbocation further, but how could we get the final product, or the alcohol product, next? Well, these electrons could then bond to the carbocation. Now in this case, we've had water add to carbocations before. In this case, we have hydroxide acting as a nucleophile. And that arrow movement would give that there, would it not? 2 lone pairs left. Okay. We have 2 steps here. The first step, can we give it a name? Could we a descriptive name for what happened? Yes. Ionization of the leaving group. The leaving group ionized away, ionized off. It left to form 2 ions. Is that possible? Can a group just leave? What happens if you put HBr in water? Well, let's don't include water in this, but doesn't the HBr ionize? And if this just leaves, and if that leaves, we produce H+. Okay, H with no bond, and then the Br takes on a 4th lone pair. There you go. Ionization. Leaving group leaving, except here it's leaving from an H. Here it's leaving from a carbon. Two steps. If we do a reaction coordinate diagram of this, we would have let's call that A, B, carbocation intermediate, and final product C. A, carbocation intermediate B, and then C. How does C compare to A in terms of energy? Pretty similar. We are just replacing one sigma bond with another sigma bond. We could get out our calculator, but I'm going to say they're pretty darn similar. We're going to make it about equal to A. Okay. Ionization to form carbocation. And then Next, oh, we're falling back downhill. This should be easy, just a little bit of energy and bam. And so this here should be your overall activation energy. The first step looks more difficult. The first step is your rate determining step. Ionization to form the carbocation, rate determining step we would expect. Nucleophile adding to carbocation should be fast. Okay, going back downhill, transition state should be fairly low. Should be a fast step. By the way, we named the first step ionization of leaving group. The second step, nucleophilic addition to carbocation. Now that step we have an addition. Overall it's a substitution reaction. So the nucleophilic addition to carbocation should be a fast step. Okay. This mechanism, what do we think about it? My main question is, what do you think about this? This is a primary carbocation. Primary carbocations are typically bad, not great. Okay? We want to avoid them, just like with alkene reactions, we avoided them. All right? We never want to make a primary carbocation unless we pretty much have to. Secondary and tertiary, better, with tertiary being the best. Of course, tertiary that is also resonance stabilized would be even better. Okay. Other thing, this mechanism is called SN1. Why? It has to do with how many of the two reagents are involved in the rate determining step. Question, is the hydroxide involved in the rate determining step? And the answer is no. Only the alkyl bromide. Because the rate determining step just involves the leaving group of the alkyl bromide leaving to form the carbocation. Hydroxide is not involved. Only one molecule of the two reactants is involved in the rate determining step. Thus, this mechanism that we showed here is called a SN1. It's a substitution by a nucleophile, but it's unimolecular. Okay? Unimolecular. We will compare that to below bimolecular. Okay. Ultimately, the first mechanism here is not the mechanism for this reaction. This is a possible substitution mechanism. This mechanism is not good for primary carbons, because primary carbocations are not good. As we move forward, we'll clarify many of these points about our mechanisms. Let's look at the other possible mechanism, or another possible mechanism for this reaction. Okay. I'm going to have to go ahead and pretty much show it to you. And it will be an SN2. Another way to get these products is, what if we just take these electrons and come in here and attack that carbon and kick these off. What does this arrow movement give? Well, this arrow movement gives those products. Electrons may bond to carbon. There's 2 lone pairs remaining. The other lone pair is now bonded to carbon. These electrons move on to bromine to become the 4th lone pair in bromide. This would be a concerted. These 2 arrows are happening at the same exact time, concerted with no intermediate. Now if we did a reaction coordinate diagram here, we would have A, and this would just be B, A, and B, and we would just have a transition state. And this here would be your activation energy. No intermediate. Up here, B was an intermediate. Don't confuse this B versus this B. This B is the final product. In hindsight, maybe I could have called this A, I, and B, with I being an intermediate, and then here there'd be just A and B with no I, or no intermediate. Okay. Which step is the rate determining step here? Well, it's only one step. It's got to be that step. That's the rate determining step. Okay. Of the 2 reactants, how many of them are involved in this rate determining step? Well, there's only one step. They better both be involved. Indeed, they are. That's why it's called substitution by a nucleophile, substitution nucleophilic, but bimolecular, SN2. This is a concerted mechanism. This is also our, if you remember, our backside attack. Okay. We have a nucleophile making a bond to carbon. If you remember, we have 2 different ways for nucleophiles to make bonds to carbons. Attacking carbocation. All right, remember this handout? All right, but we can also do nucleophilic displacement of a leaving group via backside attack. All right. And there's also stereochemistry involved with both of those that we will address as we move forward. But it will not be much new because we already have seen the stereochemistry for these types of elementary steps. We can recall, why would hydroxide attack a carbocation? Well, it's just physics. Minuses like pluses. Why would hydroxide attack a neutral carbon? Well, that carbon, okay, there's a dipole here. It's not a formal positive, but it's partial positive. And so the hydroxide is attracted in this case to the partial positive, and then we just move these onto the bromine. It's pulling them anyway. All right, and this chemistry takes place, and we replace one group with another. Okay, I'm not sure what else we can say here. I think we covered it. Now this here is the mechanism for this reaction. Okay. Now I present, these are our two mechanisms. All right. SN1 and SN2. I present them both here at the outset. Many instructors will only present maybe one. That is, this reaction will often start with like just SN2 and talk about SN2 for maybe 2 or 3 days. I present them both at the outset, and we talk about the differences as we move along. That's the way I do it. This is an SN2 example of an SN2 reaction or SN2 mechanism. Okay, I'll move ahead. There's probably other things we can say. Okay. Basically, knowing the details of these two substitution mechanisms is a must before going forward. All right. Rate determining step, fast step, concerted, transition states, intermediates, etc. All right, let's talk about kinetic studies. Now, we've already kind of talked about this up here. We'll just kind of point it out again. Kinetic studies have shown that the rate of the above reaction, okay, this reaction here, the reaction we're doing, the rate can be affected by changing the concentration of either the alkyl bromide or the hydroxide. You change the rate of either one, you change the rate of the reaction. Thus, the rate depends on both the concentrations or the concentration of both substrates. Thus, each must be involved in the rate determining step, and the reaction is indeed bimolecular. Okay? That is, there's data that confirms the mechanism. All right. Now I'll paraphrase this again. Data from the lab tells us that both substrates, the concentration of both affect the rate. That tells us that the mechanism is indeed SN2. And not SN1. If it was SN1, okay, here the rate is only dependent on the alkyl bromide. If you change the concentration of the hydroxide, the rate of this reaction should not change because the hydroxide is not involved in the rate determining step. But down here, both are involved in the rate determining step. That's why we call it SN2. Thus, if you change the concentration of either one of these, you should change the rate. And indeed, that's the observation we have from lab. Okay? The rate equation for the SN2 is, if you remember such from Gen Chem, the rate equals some type of constant times the concentration of the alkyl bromide times the concentration of the hydroxide. That is, again, SN2. Where the rate here equals K times alkyl bromide, and that's it. No hydroxide up there in the rate equation. Okay, which mechanism matches the above kinetic observations? We've already explained that a couple of times. It is SN2. What is the rate equation for the other mechanism? Well, we just stated that here. It is just K times alkyl bromide. All right. Okay. As we go along, we'll try to point out what is really with this K. Okay, it's a constant for a given reaction, but what is all that based on? Okay, it's not the concentration of the alkyl bromide. Rates of reactions are based on more than just concentrations. They're also based on reactivity factors. For example, if we change the Br to a chlorine, okay, the rate will change. All right, you have the same concentration, but the change of the leaving group would be something that's built into that K factor. All right, let's bring in some stereochemistry, proving determining mechanism by stereochemistry. Let's look at this reaction. A little bit different substrate. We've got an extra methyl here compared to here. That thus gives us now a chiral carbon, and we have a R configuration. The leaving group is on a chiral carbon with R configuration. We have hydroxide. Okay, I deliberately showed this differently. Here I just showed hydroxide without the cation, no sodium or potassium or lithium. Here I showed potassium. You got to see these as the same things. Get rid of the spectator ion. This is hydroxide. Okay? Different ways to show the same thing. If you react these together, the hydroxide will react and substitute or displace the bromide. Hydroxide is now bonded to the tetrahedral carbon. All right. We produce bromide. When you see this, you got to see that this is K plus and Br minus. Okay. These are the same. In terms of stereochemistry, if this is R, the product here is S only. Indeed, that's S. That is, the reaction is enantioselective. Only S is formed here. Thus, this reaction is known to give complete inversion of stereochemistry. Okay? But I think we knew this already. If we look back to our mechanism sheet from test 2, okay, the nucleophile is going to bond to the opposite side from the leaving group. It's a stereoselective outcome. Okay? More precisely, it's enantioselective. This is due to backside attack. But this is called inversion of the stereochemistry. Okay, a couple of questions. First off, is an SN1 mechanism more or less likely for this reaction compared to previous? What is the mechanism? Well, we kind of already know because I really stressed this early on. Okay, we already kind of know that you get backside attack with SN2. Okay, all right. And so the setup is a little bit sort of given away because of the knowledge you have already from here. But let's just answer this question. Is an SN1 mechanism more or less likely compared to previous? Okay. The previous was a primary alkyl halide. All right. This is a secondary alkyl halide. Well, it's more likely. SN1 involves carbocation, right? Right, here we go, SN1, all right, primary bad. Here it would be secondary. If that just left, we'd make secondary, and that would be more likely. Yes, more likely. But which mechanism does the stereochemical outcome support? Well, clearly it is SN2 because we see that we have inversion of stereochemistry. All right. If it was SN1, what would be the outcome? Okay, well, right here. If we attack carbocation, we attack from both sides and we would get racemic. SN1 would give racemic. We did not get racemic. We got inversion. The mechanism of this reaction is thus proven to be SN2 by stereochemistry. Okay, let's take a closer look at why or how inversion is obtained. Let's look at the 5-coordinate SN2 transition state, aka the activated complex, a term you may have used in Gen Chem, including the 120-degree bond angles and sp2-like character of the transition state. Here is the starting material, alkyl bromide R. This is R. It's just been turned a little bit and the undrawn H has been drawn in. SN2, we know that hydroxide comes in backside. The bromine is in the plane to the right, so the hydroxide negative comes in over here right between the methyl and the H. The methyl's going back, the H is coming forward, sort of like this, okay? And the hydroxide comes right between them, okay, in the plane. Right between them, and in a concerted manner kicks off the leaving group. And ultimately, let's first draw the product here. Product, there's the carbon, the OH is bonded this way, because if the leaving group is here and this comes in and kicks off the leaving group, then this group is now on the left. All right, comes in here and boop. This bond is now on the left. The leaving group is gone over there. Okay, here's the carbon. I'm not going to draw a C, but it's just kind of there. This group is going to be like this. The methyl is going to be still back, and the H is going to be still forward. But they have been inverted, okay? Sort of like here. I can't do it here. This comes in and kicks that off, but these groups have to be inverted, like an umbrella. Make room, and they come in, and this goes like this. In the event, we'll look at this. We'll look at this closer here. That is R, and guess what? That's S. Okay. Now, you guys tend to think, or after reading, you will come to think incorrectly that, well, the methyl is back. If we invert it, it has to be forward. No. We go from R to S. Is this S? Oxygen 1. Carbon with extra carbon 2, then methyl. 1, 2, 3 clockwise, the H is forward, reverse that to S. That is S. Okay, but let's look at the transition state. I'm going to have to draw in this carbon here. There's the H. There's the methyl. There's the ethyl. And this is meant to be planar. Okay, like planar. That H is really eclipsing that methyl. All right. Plane. And in the transition state, we have a bond forming here between the O and the carbon. And we have a bond breaking between the carbon and the bromine. So as the bond is forming, it's like a half a bond. And as the bond over here is breaking, it goes from a full bond to like a half a bond. We also have charge. Hydroxide is negative. It ends up being neutral. What's in between? As it's forming, it's only partial negative. Bromide is neutral. But when it's done, it's minus. What's between neutral and minus? A partial minus. And this is our transition state, sometimes with the sort of a double dagger activated complex, but it's sp2 like trigonal planar. All right, the three groups there, other than the nucleophile and the leaving group, are trigonal planar arrangement. And the bond angles between them, 120 degrees, like between the methyl and the H, or between the H and the ethyl. Where over here, 109.5 degrees. And over here, 109.5 degrees. You know, but like between the methyl and the H. All right, back over here. This was just the transition state there. Importantly, the angle let's just say angles increase. The angles around the three groups increase in the transition state. Okay, those groups are kind of like this. Nucleophile comes in, they first straighten up. All right, they straighten up. The leaving group is still semi-attached. Okay. Everything here is planar. But when this goes off, these groups actually then move that way some. I can't move my fingers that way, but they go from being here, they straighten up right here. Then they move that way to make room for the new group. And that is what is an inversion. Now 99% of the time, R will go to S or S will go to R. And pretty much for us, that will always happen, R to S or S to R. But it doesn't have to, because that really depends on what the new group is. Okay, effect of the transition state. The transition state requirement, what is the requirement? The requirement is that it go trigonal planar. Okay? This is the requirement. But the going trigonal planar can affect rates. Look at the difference here between these two alkyl bromides reacting with iodide. Okay, let's get rid of the potassium. This is I minus. All right. These are both going to be SN2. All right. And they come in here and backside attack, kick this off. Transition state goes trigonal planar with 120-degree bond angles between the three groups. The rate there is, if it's considered 1, if we do it here, all right, same thing, come in here, kick that off. The rate is much slower. Why? Well, this substrate is going to have a very hard time achieving the 120-degree bond angles that are required in the SN2 transition state. Why? Because that's a 3-membered ring. And right there it looks like a 60-degree bond angle from 9th grade geometry. Okay? It looks like 60 degrees. How easy is that going to widen out to 120? How easy will that be? Very difficult. Here, the bond angle is much wider already. And it will be easier to widen to 120 compared to this one. We see that in the rate. So understanding the transition state requirement can help us understand different rates for different SN2 reactions. Okay, I think I'm going to end this first video here. Please be looking ahead. We'll move through this handout, and what we will look at is different components of the substitution reaction mechanisms. We will look at leaving groups, compare maybe bromine to iodine or chlorine. We'll look at substitution at the carbon that's being attacked. Here it was primary. We'll look at secondary, tertiary examples, things like that. We'll also look at the nucleophile. In our example reactions thus far, we've just used hydroxide, but what other nucleophiles could be used in an SN2? So we'll look at various components of the SN2 as well as SN1 reaction mechanisms. Okay guys, I'll end this first video here. It's possible that you may be able to now start looking to provide mechanisms for these reactions on the first page.